So what we're going to try to do here is we're going to try to determine the rate equation using different types of graphs. Okay, we're going to look at concentration versus time graphs and rate versus concentration graphs. Now, so far we've seen how we can determine the rate equation using the initial rates method, right? They've given us data about different experiments where we vary the concentrations of different reactants and we get different initial rates, and from that we can determine the rate. So here, let's say that we have a reaction, okay, between A and B, okay, and A and B react to form products, okay. And now, instead of carrying out multiple experiments, I want to determine the order with respect to, let's say, A. I want to determine the order with respect to A, okay, in a single experiment. Okay, I'm just going to carry out a single experiment and I want to determine the order with respect to A. The way I can do that is by determining the effect that A has, okay, the concentration of A has on the rate of the reaction, right? Over time, for example, if the concentration of A has no effect on the rate of the reaction, I know that it's zero order with respect to A. If the rate is directly proportional to the concentration of A, I know it's first order with respect to A. And if the rate is directly proportional to the square of the concentration of A, I know that it's second order with respect to A. So what I can do is, over time, in a single experiment, over time, as the concentration of A decreases, I can determine the effect that that decreasing concentration of A will have on the rate. I can determine the effect of the concentration of A on the rate of the reaction. However, what I'm going to do here is I'm going to use a large excess. I'm going to use a large excess of B. Okay. So for example here, right, if I started with 1 mole of A, right, let's say I'm going to use 100 moles of B. Now as the reaction reaches completion, right, at the end of the reaction, we're going to have 0 moles of A left and 99 moles of B left. So what we can say over here is that the concentration of B remains constant throughout the reaction. It barely changes. It goes from 100 to a 99. Right? But we can assume that it remains constant. It's almost the same as it was at the start. Whereas A, the concentration of A decreases by 100%. The concentration of B decreases by 1%. So what we can say over here is that the concentration of B will have no effect on the rate of the reaction. As the reaction proceeds, the concentration of B remains constant. So what we can say is that over the course of the reaction, only the concentration of A is decreasing. And we can determine the effect that decreasing concentration has on the rate of the reaction. And from that, we can determine the order with respect to A. So the reason we're using a large excess of B here is to ensure that the concentration of B remains constant over time. Okay, it remains constant over time. We want to do that to ensure that the concentration of B has no effect on the rate of the reaction. Okay, since we're trying to monitor the effect of the concentration of A. Okay, so now let's say that I monitor the concentration of A over time. Okay, Okay, so here I have a graph of the concentration of A, right, against time t, right? And what I see is that this graph is a straight line. So the concentration of A decreases linearly over time. So over here, we know that the slope of a concentration time graph, right, that's the change in concentration with respect to time, right? The slope of this concentration time graph, the slope is the change in concentration over the change in time, right? The slope, or the absolute value of the slope, is the rate of decrease of A, right? The absolute value of the slope is the rate over here. Now we know that since we have a straight line of concentration versus time, a straight line has a constant slope. So that means the rate of this reaction remains constant throughout. When I had a higher concentration of A, even when I had a lower concentration of A, the slope remains the same. So the rate remains constant. We have a constant slope or we have a constant rate. So what we're saying is that as the concentration of A decreases, the slope remains the same. So that means that the rate remains the same. So we can say that the concentration of A has no effect on the rate. We have a constant rate throughout, no matter what the concentration of A. So what we can say over here is that if we look at a graph, of rate versus concentration of A, look at a graph of rate versus the concentration of A. The rate is just the absolute value of the slope, and the rate is a constant throughout. The rate is a constant, so it's a horizontal line. It's a horizontal line. So over here, we can see that the concentration of A has no effect on the rate, right? No matter what concentration of A you have, the rate remains constant. The slope of the concentration time graph is a constant. So here we can say that it is order 0. It is order 0 with respect to A, or 0 order with respect to A. Just note over here that if you look at the rate equation then, right, it will be K times the concentration of A to the 0th power, and we don't know the order with respect to B. Okay, here we're just determining it for A specifically. Here we're determining it for A specifically. Okay, so we're just using a large excess of B. For B, we'll have to do a separate experiment to determine the order with respect to B. So here in this particular experiment, we're only determining the order with respect to A. So if we look at specifically the order with respect to A, we know that the rate will simply be a constant, right? Because A to the power of 0 is just 1, right? We're not looking at the effect of B here. Okay, so we're not looking at this right now. So again, this is not the actual rate equation. This is just showing us the effect of the concentration of A on the rate. Okay, so here what we're saying is that the rate remains constant, okay, with respect to the concentration of A. Okay, so this is not the actual rate equation. For the actual rate equation, we'll have to also determine the order with respect to B as well. So, but we know definitely that if we get a graph like this, that A will not show up in the rate equation. Okay, and the rate will be constant with respect to the concentration of A, since it has no effect on the rate. And the concentration time graph will be a straight line. Okay, the concentration of A versus time. So now let's say that the reaction is order 1 with respect to A. Let's say that the reaction is order 1 with respect to A, right? Or we can say it's first order with respect to A. It's first order with respect to A. Okay. Now what we're going to see is something like this. What we're going to see is something like this. If we look at the concentration of A over time, okay, it will decrease like this, right? Decrease like this. Over here, we know that the rate is directly proportional to the concentration of A. So initially, we have the highest concentration of A, so the slope is the steepest. Over time, as the concentration of A decreases, the slope of the concentration time graph becomes less steep. It's steepest at the beginning, and as the concentration of A decreases, the slope of the concentration time graph, right? Remember the absolute value of the slope, right? That is the change in concentration over the change in time, right? That is your rate. So over time, what's happening is that as the slope becomes less steep, the rate is decreasing, because you know that the rate is directly proportional to the concentration of A. Lower concentration of A means slower rate of reaction. And here, since the rate is directly proportional to the concentration of A, right? The rate is directly proportional to the concentration of A. We can say that the rate versus concentration graph is just a straight line, right? If I double the concentration of A, the rate will double. If I triple the concentration of A, the rate will triple. So the rate is directly proportional to the concentration of A. The rate versus concentration graph looks like a straight line. So what we can say over here is that the rate is directly proportional to the concentration of A, right? That is basically saying rate is equal to K times the concentration of A, right? So that is Y is equal to mx, right? Here X is the concentration of A, rate is your Y over here, so Y, that's the rate, is equal to M, that's the K over here, times X, right? So what we're saying over here is that this graph will be a straight line, right? Y is equal to mx. Again, this is not the actual rate equation. Here we're just looking at the effect that the concentration of A has on the rate. And we know that if it's directly proportional, that means that the rate versus concentration graph will be a straight line. So now let's look at a reaction that is second order with respect to A. So instead of it being first order with respect to A, let's say that now it is order equal to 2 with respect to A. Now again, if you look at the concentration time graph, it look very similar to the concentration time graph that you had for a first order reaction, right? Because over time, as the concentration of A decreases, the rate will also decrease, right? So we can say that over time, the rate of decrease will decrease, right? The slope will become less steep, so it increases fastest at the beginning, and then it gentles down like this, right? It becomes more gentle, the slope. So we can say the rate of decrease is fastest, and as the concentration of A decreases, the rate of decrease also decreases, right? So the graph looks very similar to a first order graph, okay, but it's a little bit steeper, right? Because it's more dependent on the concentration of A. And the rate versus concentration graph, looks like this. So this is what the rate versus concentration graph looks like. Okay, so here we have rate versus the concentration of A, right? Now we know in this particular case, because it's order 2 with respect to A, we know that rate is directly proportional to the concentration of A squared, right? So this is sort of a parabola, okay? But you're only looking at the positive side of the parabola, right? So you have a y is equal to x squared graph, okay? But again, we're only looking at the right hand side of the origin, so therefore we see a graph like this, okay? So but this is basically the right hand side of a y is equal to x squared graph. So now if we were to summarize, right, if we have a reaction like this, and again we're trying to determine the order with respect to A, right? If we look at the concentration versus time graphs, right, if its order equals 0, right, it's 0 order with respect to A. If it's 0 order with respect to A, then we can say that the graph would look like this, right? We can say that over time, we'd have a constant rate of decrease. We would have a constant rate of decrease. So that is concentration of A versus time. On the other hand, if it was order equal 1 with respect to A, or in other words, it was first order with respect to A, right? If it was first order with respect to A, you'd have a graph like this. Concentration of A versus time, right? And our graph would look like this, right? We have a graph that looked like this. Okay, so this is what the graph would look like for a concentration time graph if it was order 1 with respect to A. And if it was second order with respect to A, right? So order was equal to 2 with respect to A, then the graph would look like this. It would look very similar to the first order graph. It would look very similar to the first order graph. You'd have a very similar looking graph, but you'd have a much steeper rate of decrease, right? Something like this. All right. So these graphs look very similar. But in the first case, it's order equal 1, and now it's order equal 2, or it's second order with respect to A. Now, how do we differentiate between first order and second order reactions just by looking at a concentration time graph? Now, to understand how we can differentiate between order 1 and order 2 reactions, or first order and second order reactions with respect to a particular reactant, okay, we're going to look at something known as half-lives. Okay, so what is the half-life? Okay, half-life is defined as the amount of time taken for a reactant to reach half its original value. And the symbol that we use over here is T half, okay, T subscript 1 over 2. So here, if we look at the half-lives, okay, if we look at a half-life, right? We can determine the half-life. We can determine the half-life from a concentration versus time graph. So here we have concentration versus time graphs, right? And we have graphs that are that this is what a graph of concentration versus time would look like if the reaction was zero order with respect to it. This is what it would look like if it was first order with respect to it, and this is what it would look like if it was second order with respect to it. So let's say that each of these cases, so over here, let's say that we want to say that, we want to determine whether it's order 0, order 1, or order 2 with respect to A, right? 0 order, first order, second order. And I say that my rate of decrease is 2 moles per dm cube per minute. Okay, 2 moles per dm cube per minute. Okay, that's the initial rate. That's the initial rate in these cases. Okay, and let's say that first we're going to look at a reaction that's 0 order with respect to A. And let's say that my initial concentration is 4 moles per decimeter cube. Okay, my initial concentration is 4 moles per decimeter cube. Now, after the first half-life, right, my concentration will be 2 moles per decimeter cube, right? Because, again, that's the amount of time taken for the concentration to reach half of its original value. So we started at a concentration of 4, and now we have a concentration of 2, right? So this is my first half-life. This is my first half-life, okay? And then my second half-life would be the time taken to go from 2 to 1, right? So this is my second half-life. This is my second half-life. Now, my rate over here is 2 moles per decimeter cube per minute. So how long is my first half-life? How long is my first half-life? My concentration is decreased by 2 moles per dm cube, right, from 4 to 2. So how long did that take? It took us 1 minute, right, because concentration is decreasing at 2 moles per dm cube per minute. So this was 1 minute. That was the first half-life, right? And how long is the second half-life? We're going from 2 to 1. So the concentration is decreasing by 1 mole per dm cube per minute. It's decreasing by 1 mole per dm cube per minute. So now it will be 30 seconds, right? Half a minute. It's going to be half a minute. Now the reason why the rate is remaining constant is because even though the concentration of A is decreasing, it has no effect on the rate. So the rate of decrease remains the same. It will decrease at 2 moles per dm cube per minute throughout because it's 0 order with respect to A. The rate is unaffected by the concentration of A decreasing, and therefore, right, we can see that successive half-lives are decreasing. We can see that successive half-lives are decreasing. So over here we can say that if the reaction is 0 order with respect to A, we can say that successive half-lives are decreasing. Successive half-lives are decreasing. What that means over here is that the first half-life will be longer than the second half-life, right? And the second half-life will be longer than the third half-life, and so on. The successive half-lives are decreasing. Again, the reason why is because even though the concentration of A is decreasing over time, the rate of decrease remains constant because it's not being affected by the concentration. So for the first half-life, you decreased by 2 at 2 moles per dm cube per minute. That took us a minute. For the second half-life, you decrease the concentration by 1 at 2 moles per dm cube. That takes us half a minute. So the second half-life is shorter than the first half-life. And the third half-life is going to be 0.25 minutes, and so on, right? The successive half-lives are decreasing. Now let's say that the reaction was first order with respect to A. And again, we have an initial concentration of 4 moles per dm cube. Okay. Now over here, right, after the first half-life, our concentration will be 2 moles per dm cube, right, after the first half-life. So this is our first half-life here, right? And then after our second half-life, our concentration will be 1 mole per dm cube. Right? So this is our second half-life. Right? This is our first half-life, and this is our second half-life. Now, over here, right, it's, again, let's say our initial rate of decrease is 2 moles per dm cube per minute. So in our first half-life, after our first half-life, right, our concentration had decreased by 2 moles per dm cube per minute. So we started with 4, and we ended up with 2 after the first half-life. So that took us that took us 1 minute because we were decreasing at 2 moles per dm cube per minute. So that took us 1 minute. Okay. Now, what about the second half-life? Now, what if you notice, we've halved the concentration of A. We had a concentration of A that was 4 moles per dm cube. Now the concentration of A is 2 moles per dm cube. So that means if I've halved the concentration of A and it's first order with respect to A, it means that I've also halved the rate of decrease. I've also halved the rate of decrease. So after the first half-life, my rate of decrease is now 1 mole per dm cube per minute, right? Because the rate is directly proportional to the concentration of A. Because the rate is directly proportional to the concentration of A. Initially, I had a concentration of 4 mole per dm cube. My initial rate was 2 mole per dm cube per minute. I halved the concentration of A. My rate of decrease is now 1 mole per dm cube per minute. And for the second half-life, I'm decreasing the concentration by half the amount, by minus 1 mole per dm cube, but the rate is also half as much. So again, it will take us a minute, right? Because initially our rate was 2 moles per dm cube per minute. So it took us 1 minute to go from 4 to 2, to change by 2 moles per dm cube. Now that the concentration of A is halved, our rate is halved, but obviously we're decreasing the concentration by 1 mole per dm cube a minute. So we can say that the second half-life is the same as the first half-life, right? The second half-life is the same as the first half-life. So over here, we can say that successive half-lives are constant. Successive half-lives are constant. Okay. And for a first order reaction, if it was order 1 with respect to a particular reaction, we can say that the half-life is independent of the concentration of A. The half-life is independent of the concentration. Okay? Because no matter what the concentration, whatever concentration you're starting with, the half-life will always be, whatever concentration you're starting with, the half-life will always be 1 minute for this particular reaction. Okay? At a particular temperature, obviously. So the half-life is independent of the concentration of A. And then if it was second order with respect to a particular reactant, if it was second order with respect to a particular reactant, then what you would see is something like this. Okay? You would see something like this. You would see that successive half-lives are increasing. Successive half-lives are increasing. Okay? It's the opposite of zero order. Okay? So here you would see that successive half-lives are increasing. The reason why is initially, again, let's say our rate of decrease is 2 moles per dm cube per minute. So the first half-life would be, let's say, 1 minute, right? Because it's decreasing by 2 moles per dm cube, so that would take us 1 minute. But then the concentration of A is halved, right? So the decrease from 2 to 1, right? The second half-life, we're decreasing the concentration by 1. But because the concentration of A is halved, we have 1 over 2 times the concentration of A now. The rate will be 4 times slower, right? We've decreased the concentration by a factor of 2, so the rate will be 4 times slower, right? So now instead of being 1 mole per dm cube per minute, the rate will become 0.5 mole per dm cube per minute. So it'll actually take us 2 minutes for the second half-life, for example, rather than 1 minute. So we have increasing half-life. The third half-life will be longer than the second half-life, it will be longer than the first half-life. So again, the idea here is that if the first half-life is, let's say, 1 minute, then the second half-life would be somewhere close to 2 minutes, and so on, right? Successive half-lives would be increasing. Now, of course, we've also learned that we can just look at a rate versus concentration graph. Okay. We can look at a rate versus concentration graph as well and determine the order. Again, this is just a summary that we're providing here. So we can say that if the concentration, right, or if the rate does not depend on the concentration of A, right, if the rate does not depend on the concentration of A, then we know that it's zero order with respect to A. Zero order with respect to A. If the rate increases linearly with the concentration of A, then it's first order with respect to A. If the rate increases linearly, right, the concentration of A, then we know that it is order 1 with respect to A. And if the rate increases exponentially, sort of like y is equal to x squared, right, the right hand side of a parabola, if it increases like this, then it is second order with respect to. So here you have rate versus concentration. Okay, this is order equal to with respect to A. So again, if you just look at a concentration versus time graph, right, we know that it's order 0 if the concentration decreases linearly with time. The rate of decrease remains constant over time, so it is going to be order 0 or 0 order with respect to A, right? Whereas first order and second order graph looks very similar, or they look very similar, right? To the concentration time graph, so you have to determine whether it's first order or second order using half-life. If the half-life is constant, right, start with the initial concentration and see how much time it takes to get to half that, and then see how much time it takes to get from, let's say, like 2 to 1. And if the amount of time taken for each successive half-life is the same, it's independent of the concentration, then we know it's first order. If successive half-lives are increasing, then it's second order. Okay. Whereas for rate versus concentration graphs, is very visible, right? If the concentration of A has no effect on the rate, it's 0 order. If the rate is directly proportional to the concentration, it's first order. And if rate is directly proportional to the square of the concentration, if you have a sort of exponentially increasing graph, like a parabola, then it's second order. The next thing that we have over here is this. Let's say that I have a reaction. Okay, let's say that I have a reaction again between A and B to form products. Okay, but now I'm telling you that the rate equation for this reaction is equal to K times the concentration of A. So I've determined the order with respect to A, and I've determined the order with respect to B. And what I've said is that this reaction is first order with respect to A and 0 order with respect to any other reactants and catalysts or whatever I might be using. But this is what the rate equation looks like. Okay, so I can say that obviously it's first order with respect to A, and the overall order for this reaction is also 1. For this sort of a reaction, the rate constant K is equal to 0.693 divided by the half-life. Okay, or you can say that the half-life is equal to 0.693 divided by the rate constant. Now, if you look at the expression for the half-life here, we can clearly see that the half-life is independent of the concentration. It only depends on the rate constant here. Okay, so again, we can say that the half-life is independent of the concentration. And in this particular case, if you notice, the units of K are rate divided by concentration, right? Because you have rate divided by concentration to the power of 1. The units of K are simply moles per dm cube per second divided by moles per dm cube, right? So the units of K come out to per second. Okay, so the units of K come out to per second, or in some cases it could be per minute, depending on what information is given to you about the half-life or the rate. If the half-life is given to you in seconds, then it will be per second, the units of K. If the half-life is given to you in minutes, then the units of K will be per minute. And we can see that in the expression over here. Again, this expression here for half-life. We can determine the half-life, okay, using the rate constant, or we can determine the rate constant using the half-life directly if we have a reaction that's first order with respect to a single reactant and 0 order with respect to all other reactants. Okay, so the overall order is also equal to 1. It only applies if both of these conditions are met. Here, of course, T half is just the half-life of A.